Hello, this is mathjazz from Almost Cool. This is our third derivative quiz. Our topic today is implicit differentiation. I will read the questions, then you can pause the video and work out your solutions to them. And when you're done, unpause the video and I will be here with the solutions. So, without further ado, question 1. Find dy dx for the following equations. A. X squared plus y squared equals 9. B. Y squared plus x cubed equals x squared. C. 8 equals 4y plus x squared y. And question 2. Find the tangent lines for the equation x cubed minus 9 halves xy plus y cubed equals 0 when x equals 1. I'm calling this a bonus question because it is more difficult than I intended when I wrote it down when I was going through and solving it. But if this is hard, then I have a simplified version here. Find the tangent line for the equation x cubed minus 9 halves xy plus y cubed equals 0 at the point 1, 2. It turns out that this equation intersects the line x equals 1 3 times. So the simplified version, it will only look for the tangent line at one of those 3 points instead of all 3 of them, and it gives you the y coordinate for the particular point that you're looking for. Whereas in the bonus question version, you not only have to figure out that the tangent line that this equation has 3 intersections with the line x equals 1, but you have to find the y coordinates for each of those points. So, without any further ado, here are the solutions. 1a. Find dy dx when x squared plus y squared equals 9. We're going to start by taking the derivative of both sides of the equation. We'll use the power rule on the left-hand side, and we know that the derivative of a constant is 0 for the right-hand side. So we get 2x plus 2y dy dx equals 0. We subtract 2x to the other side, and then we divide both sides by 2y, and the 2's will cancel, so we're left with dy dx equals negative x over y. 1b. Find dy dx when y squared plus x cubed equals x squared. We take the derivative of both sides of the equation, using the power rule on both sides. We get 2y dy dx plus 3x squared equals 2x. And then when we move all of the terms that do not have dy dx's to one side, we get 2y dy dx equals 2x minus 3x squared. We divide both sides by 2y, we get dy dx equals negative 3x squared minus 2x over 2y, and I decided to factor a negative 1 out of the top so I could have a positive leading coefficient in the numerator and have that coefficient be the coefficient of the highest power. You didn't have to do that. It was purely aesthetic. Question 1c. Find dy dx when 8 equals 4y plus x squared y. We're going to take the derivative of both sides using the power rule. We get 0 equals 4 dy dx plus 2xy plus x squared dy dx. That's using the product rule on the term x squared plus y. We now move all of the terms that have a dy dx to one side, and the terms that don't, or the term that doesn't, I should say, we leave on the right-hand side. We factor out the dy dx, and then we divide by negative 4 minus x squared, so we get dy dx equals negative 2xy over x squared plus 4. Question 2. I'm going to solve the bonus question version, and I'll point out the parts that are useful for the simplified version. First, we're going to take a look at the graph of this equation. So, this is a graph of the equation. Notice the line x equals 1, the vertical line x equals 1, crosses this graph at 3 different points. So that's what I was saying earlier. We're going to have to figure out the y coordinates of each of these points. And we're also going to have to find the derivative of at each of those points. Fortunately, we can find the derivative of this equation and then plug in the points separately. We don't have to find a derivative at each point. We can find the general form of the derivative and then just plug in the points and get the value of the derivative at those 3 points. So first we'll find dy dx. We take the derivative of both sides. This uses the power rule and the product rule to get this. So 3x squared minus 9 halves y minus 9 halves x dy dx plus 3y squared dy dx equals 0. We combine all of the dy dx's on the left side of the equation, and all of the terms that do not have dy dx's in them go to the right hand side. So we get negative 9 halves x plus 3y squared times dy dx, since we factored out the dy dx, equals negative 3x squared plus 9 halves y. We divide the both sides of the equation by the coefficient on the dy dx, and I factored out a negative sign and canceled a negative sign in the numerator. So we get dy dx equals 3x squared minus 9 halves y over 9 halves x minus 3y squared. We will now find the y coordinates of the points by plugging x equals 1 into the equation and solving for y. So we get 1 cubed minus 9 halves times 1 times y plus y cubed equals 0. This gives us 1 minus 9 halves y plus y cubed equals 0. Now, if we clear all the denominators of our equation, so that we have integers as our coefficients, we can then use the rational roots theorem to find what the possible rational roots of this equation are. So I multiply everything by 2. Of course, 2 times 0 is still 0, so the right-hand side doesn't change. But I multiply everything by 2 here, so that I get 2 minus 9y plus 2y cubed. There's an error on the slide. That should be a negative sign in front of the 9. And then we can use the rational roots theorem to find the roots of 2 minus 9y plus 2y cubed. The roots of that polynomial will also be the roots of the 1 minus 9 halves y plus y cubed equals 0. So we use the radical roots theorem. First, we make a list of the factors of the leading coefficient, that is, the factors for the coefficient for the 2y cubed term. Factors of 2 are 1 and 2. Then we find the factors of the constant term, which is 2, so its factors are 1 and 2. We divide the factors of the constant term by the factors of the leading coefficient, and we take both the positive and negative values for each of these numbers. So we get the list plus or minus 1/2, plus or minus 1, and plus or minus 2 as the possible rational roots of this polynomial. What we'll do now is plug each of these values into our polynomial and see which of them balances the equation. If any of them balance the equation, then the values that do will be roots of this polynomial, which means that we can then factor out y minus that value from the polynomial. So we'll start with y equals 1. I like to start with the integer values rather than the fractional ones, and I usually start with the smallest integer values. So y equals 1, we plug into the equation. We get negative 5, but that's not 0, so we try again. We plug in negative 1, we get 9, which isn't 0. The equation still doesn't balance, so we move on again. We plug in 2, we get 2 minus 9 times 2 plus 2 times 2 cubed, and that is 18 minus 18, which is 0. The equation balances. Now, in the simplified version of this question, I gave you that we're looking for the point, or sorry, we're looking for the tangent line at the point 1, 2. So that was actually spoilered already for us, but that was how we found out that 2 was in fact a root of this polynomial. Once we have a root, we can now factor the original equation and use the rational roots theorem or the quadratic formula to try and find remaining roots. In this case, when you factor out a term from a quadratic, you'll be left with when you factor out a term from a cubic, you'll be left with a quadratic, and we can use the quadratic formula. So that's how we'll proceed from here. Because the quadratic formula always works on quadratics, whereas the rational roots theorem only works when there is a rational root. Not all roots are rational. So we factor out y minus 2 from our polynomial 2 minus 9y plus 2y cubed, and we get y minus 2 times 2y squared plus 4y minus 1. And we can use synthetic division or long division to do that. Or we can even do factoring by grouping to do that. And those will be topics for another video. So we use the quadratic formula on this 2y squared plus 4y minus 1 polynomial, and we find that its roots are -1 plus or minus the square root of 6 over 2. So now we have all three roots of our polynomial, which are 2, -1 plus square root of 6 over 2, and -1 minus square root of 6 over 2. So now we have our derivative, and we have 3 points, 1, 2, 1, -1 plus square root of 2 over square root of 6 over 2, and 1, -1 minus square root of 6 over 2. If we plug each of these 3 points into our derivative, we get the slope of the tangent line at each point. Once we have the slope at each point, we already have the point, so we can plug the slope and the point into point-slope equation for a line and get the equation for the tangent line at each point. So we do that. At the point 1, 2, we plug 1, 2 into dy dx, and we get 4/5. So the tangent line is y minus y naught equals m times x minus x naught, or y minus y naught equals m times x minus x naught. There we go. And plugging in 2 for y naught, 1 for x naught, and 4/5 for m, we get y minus 2 equals 4/5 x minus 1. There we go. This is the tangent line at the point 1, 2. And here's a graph of our function with that tangent line. See, it looks very pretty. Lines up with the function at the point 1, 2. Now we have to find the other two tangent lines. And we do that by plugging in our point. This time we're plugging in the point 1, -1 plus the square root of 6 over 2. We get 30 minus 9 times the square root of 6 over -12 plus 12 square root of 6 as our slope. And so we plug that into the point-slope formula. We get y plus 1 minus square root of 6 over 2 equals our slope times x minus 1. And here's the graph of the equation of that line and of our original graph. It also lines up very nicely with the graph. And our third point. So this time we're plugging the point 1, -1 minus square root of 6 over 2 into our derivative. We get -30 plus 9 over, we get -30 plus 9 square root of 6 over 12 plus 12 square root of 6. This is the slope of the tangent line. We plug it and the point into our point-slope form. We get y plus 1 plus square root of 6 over 2 equals negative 30 plus 9 squared of 6 divided by 12 plus 12 squared root of 6, there's a typo in that, times x minus 1, and we get, this is the graph of our final tangent line, and here's a graph of our original function and all three tangent lines. Thank you for watching this video. I hope that you're enjoying learning calculus, and I hope that you did well on this quiz. Contact information is on the screen. I hope that you're having a great day. Goodbye.